Welcome to Lecture 2. My name is Frank. This is still the graduate course on probabilistic programming. Okay. Let's see. What did we do in Lecture 1? Can I move this off to another screen? Yes, I can. Good.
Sorry, sir. Just a reminder to start the recording.
Is the recording not started?
Oh, it has. Sorry, I just saw a message.
Great. Let's
Take two.
Say exactly. Take 2. All right, here we go. Third one. Welcome to Lecture 2. My name is Frank. This is still the introduction to probabilistic programming graduate course here at UBC. Okay. So, Lecture 1, last time, we basically made the case that the course will be hard but rewarding, and talked a little bit about probabilistic programming and talked about it being an established and growing field. And at the end, we talked through a couple of example applications of probabilistic programming, which are kind of interesting. I encourage you, again, to download the book. This link is available, or you can just look up Introduction to Probabilistic Programming on Google, and you'll get to it. I was planning on the second lecture being a crappy lecture, but then I decided in a panic to rewrite the entire lecture this afternoon. So that means it'll probably be crappy, but in a different way. What I want to try to get across to those of you who are not familiar with it today is something about model-based reasoning. In particular, I want to think about generative models, and I want to establish, the fact that a generative model is equivalent to a simulator, and they're all, kind of part and parcel of the same thing. Generative models often have interpretable components, but not always. I want to get you to think about what understanding is and how, how you use a model to understand the world. We won't go into the mathematical details of inference or Bayesian inference in particular. We'll do that over the next few lectures. But you should be thinking all the time that there are these latent quantities, and we want to do, that we're going to think about, inference, learning, understanding, so on and so forth. All of these things are going to be framed as inference, in particular Bayesian inference, where we derive or computationally characterize a posterior distribution over latent quantities. And a generative model is one which you generate your observations. So generating from a model given samples from a posterior should reconstruct data, okay? And this is kind of a Hinton-ish idea, Jeff Hinton that is, where a standard for saying whether or not you understand some phenomena or the world, or you have a computer model that actually understands what's going on, is basically being able to generate synthetic data that is indistinguishable from real data. If you can do that, whether it's MNIST digits or computational fluid dynamics models, or again standard modeled simulators or something like that, that demonstrates a real understanding of the phenomena if you can actually generate exemplars of the phenomena and you can't distinguish them from reality. That's some notion of true understanding. I should be as clear as possible, as soon as possible, and we'll run into this problem several times, that deep learning people call the inference neural network a model quite frequently. They'll talk about models, okay? And this is a terrible, terrible abuse of terminology, because a model really is meant to be something that is a surrogate or a stand-in for reality. And it means that it goes in the exact opposite direction of what deep learning people call a model. It goes from latents to observes, okay? I also realized that in previous versions of the course, I always made people sort of learn functional programming on their own and do a bunch of homework on that. The homework this year does not include that. So I actually do need to spend a little bit of time today, even before I show you some examples today, talking about functional programming and introduce you to the rough ideas of the syntax that we'll use in the book and in the course, and we'll use for examples, and you'll have to write programs in and interpret programs in and that sort of thing. So the code examples in the course and the book are written in functional programming languages. There are 3 different languages that we play with in the course. One is a pure deterministic first-order programming language. That will be the language of the link functions, it will turn out. There's a first-order probabilistic programming language, which is basically will compile to graphical models. It corresponds to finite order probability models, and then there's a higher order probabilistic programming language, and that more or less is equivalent to any kind of modern. It's capable of representing and denoting infinite dimensional probability distributions, and has the same sort of expressivity as standard programming languages like Python, so on and so forth. All of these three languages that we'll talk about in the course to establish sort of the mathematical ideas roughly share the same syntax. There are extra exercises in the course website that are sort of at the bottom of the homework page, I think, that will get you up to speed if you're actually interested in learning about functional programming, if you're interested in Cloture, or you're interested in programming in Anglican or directly using this language straight away. You can get up to speed by doing some of those exercises. We developed them actually for participants in the DARPA program, and they're very, very well designed exercises, actually. Cool. And the syntax that we use is Cloture syntax. It's also Anglican syntax. Anglican is built on top of Cloture, but it's a Lispy style syntax with a little bit of difference from Lisp in that you use square brackets in certain cases and so on and so forth, slightly different naming conventions. So many of you, I don't believe, have any functional programming background. So I'll start you off just a little bit. The syntax is incredibly simple. The syntax is just S expressions, okay? The most important thing you need to know is that parentheses are going to be used for function application. So when you see an expression, parentheses plus 1, 1, I think you can see my cursor here. When you evaluate this expression, the meaning of this expression is 2, right? Which is to say that there is some meaning for plus, and there is some meaning for 1, and there's some meaning for 1, those tokens. And when we evaluate this expression, when we apply plus to its arguments 1, 1, we get 2. Back in the old days when we had Hewlett-Packard calculators when I was a kid, I don't know if they still do this or not, this prefix versus infix notation was also, and I don't even know, somebody should say in the chat channel whether or not this is like xenophobic or something like that. They called it reverse Polish notation back in the day. But basically, when you apply minus to 10, 3, really that's, the function minus with 2 arguments, the first one and the second one, 10 minus 3, that's 7, okay? And you can see, if you squint at at what I would refer to as an abstract syntax tree on the right-hand side of this slide, you can see something that corresponds to nesting of function applications. So I want to experiment with that's Lukasevich. Yeah, good, nice. So I want to experiment. I don't know whether or not, do you have the ability to click on my picture and make it larger or not? So in other words, if I start writing on the yes from one, no from another. So which of you is correct? Okay, so if I write out on the board here, I wonder, is this, I guess this won't happen in the video recording, will it? This is where I'm getting screwed by not being able to airdrop onto my iPad. Well, I'll do it anyway. I'll write it super huge so you can see it even when it's small. So obviously, this abstract syntax tree corresponds to the following S expression. Okay. Thank you for all your suggestions. I will stop screen sharing at various points when I really need to use the board today. Normally, I would use the whiteboard option on my iPad, but I can't do that because I'm not sharing off my iPad because the slides are too big today. Anyway, hopefully you can see that. That should be legible. Is that legible? Sweet. Okay, great. So this corresponds to the abstract syntax tree on the right-hand side of this slide. And to evaluate this, you evaluate the inners, and then you evaluate the outers, so on and so forth, applying the function times to 4, 4, times to 8, 8, and plus to the value of the inner expressions. Okay, fine. You'll get used to looking at expressions like this. They're not so bad, right? Again, the expression in the top here, where you have the function divide, and then the inner expression 10 times 2 plus 1, 2.1 plus 4.2. The inner expression divided by 2. There is a translation that you can do, right? So the point is that this upper expression has some meaning, and we will invariably talk about evaluating or what the meaning, the semantics of an expression is. And the way you do that is that you do some sort of transformation, which is known as compilation, to some other standard expression that has an agreed meaning. So we all agree, we all understand the operator precedence in mathematics. We've had it drilled into us since the very beginning of our education, right? For various reasons, the S expression syntax is nicer, easier to work with, so on and so forth. Yeah, I'm very well aware, thank you for the comment, that people who did their undergrads at UBC had to learn Racket, which is Scheme, which is Lisp, which is the same as Clojure, which is so on and so forth. But I'm willing to bet that that not everybody loved it. I'm guessing that was somewhat sarcastic. And I'm guessing that that's probably only a third of the class. So great. Such languages have all kinds of special forms. You can read them as functions if you want to, but they're really special forms. They do different things depending on the evaluators that you write, but they have the meaning that you expect. So if you can look at it as just being a conditional operation, greater than here is a function, right, that you apply to 3, 2. So is 3 greater than 2? If that's true, then return the first argument, otherwise return the last argument. So if, again, greater than or equal to is a function that's applied to 3 and 3, that's true. So it will return the value of the I guess the second argument to if, right? I should point out something kind of interesting here, which is that it doesn't matter whether you do eager evaluation or lazy evaluation. The meaning of these expressions is the same when there are no side effects. What happens if you put in too many arguments? Then you have a syntax error. In other words, you've provided too many arguments to a function, and that function you can't evaluate the meaning of that expression because it doesn't make any sense, right? What is if with 4 arguments? I don't know, right? Good question, though. Totally fair question. So here again, if greater than 4, 5 is greater than 4, it will return the first, rather the second argument, the predicate. It will return what's known as the consequent versus the alternative. It will return the consequent, and plus 1, 3 is 4. Okay, so presumably you can start reading some of these things. Christian is absolutely right. Thank you, Christian. It's a semantics error. You can parse it as syntax. That's true. Correct. Thank you for correcting my explanation. There are let expressions. These introduce bindings, just like in math. So if you're used to mathematical expressions and mathematical writing and notation, where you say let x be 10, let y be something, then evaluate something. That's fine. So here, x is bound to the value 10, y is bound to the value 2, and the return value, the value of the let expression, is the value of the last expression in a sequence of expressions here. So the last expression here is plus xy, so the value of this let expression is 12. Okay. A simple example here, x is 10, y is 2. We have another slightly more complex expression. That's totally fine. You can do in-place computation in let expression. So x is 10, y is 2. X is the value of times x3. I probably should have made that a y, but that's fine. That needs to be a y here. Oh, no, that's fine. X. So it will rebind. Yeah, never mind. That's what this is. That's what the point is. So the point of this one is x is 10, y is 2. X will be rebound to the value of the previous value of x times 3. When you add these together, that'll be 32. Okay. So this rebinding is important. So you can basically reuse variable names here, but the sequence of bindings matters actually. Okay. Cool. This last expression is an important one. This is going to be a form that we see quite a lot. So we let x and y take on particular values. Then we do something, and the value of this thing, the computation that's done here is totally irrelevant because the value of the let expression is just plus x, y, which is just 12 here. Okay. So statements like this, when you read them, they're irrelevant. They do not affect the meaning of this expression in any way. But if there are side effects, and I should have changed the font on this to be observed from our language, but you will come to understand what side effects are as we progress through the course, but observe will produce a side effect, and you might want to put statements in this position that produce side effects but don't actually change the value of the expression. And we'll see some examples of that today, and they'll be confusing, and then that confusion will resolve over the course, the term of the course. In functional programming languages, it doesn't necessarily have to be the case, but usually functions are first class. They're called lambdas, or let declares a function. No, let declares a binding, yeah, or a list of bindings. And you'll see that there's sugar. So let actually only declares a single binding, but I'm showing you examples with sugar right now. So called lambda and lambda calculus, or lambda in Lisp or Python. In Cloture, Anglican, and the languages that we have here, we have two forms. There's the keyword, reserved keyword fn, or the special form defn. And there are examples of this, which, great, these are awesome questions. So is there a reason why the entire program is in parentheses? This is a great question. Yes. The entire what is a program? A program is a function. What I've not discussed or shown here is the fact that, you know, functions may produce side effects, they may produce values, they may have arguments, so on and so forth. But so you can imagine a program that looks like this, which has no arguments. This is the entire program. Let's just go first. So defn is a special form that defines a function in a global scope called myfn that takes two arguments, x and y. You can think about this as like lazy let blocks or something like that. These are variables whose values are assigned during evaluation or when the function is applied. Okay, there's all sorts of stuff going on in the comment block. I'll let it pass. So myfn is a function that, when applied to the values that will be passed in the future, x and y, evaluates to the value of 2 times x plus y. Okay. Over here we have a let block, where my function is a lambda. It's a function. Functions are first class. So this fn returns a function of 2 parameters that produces the same value as over here. and my fn is bound to the function. When you apply my fn to the values 5 and 9, this returns 19. Okay, cool. Are there questions, or is there just a burble of people showing off what they know and intimidating and scaring everybody else who doesn't know all this stuff already? Let's let the people who may not know what we'll get great. What's homoiconic? It means that the data is code and code is data. We'll get to it in just a second, but all of these parentheses forms are list data structures. So that means that the code is actually a nested list, which means that the code is represented as a data structure in the language, and data structures in the language can be evaluated as if they were code. That's what homoiconic means. Okay. Can we apply myfn outside this let block? So no, this let block is as Christian described in the chat before. It defines a lexical binding for a constant, so that the range that my fn is usable in is only in the let parenthetical, in the let s expression. Yeah. Let defines a constant. This is so frustrating because I can't write. So let does not define a constant. Let define the value. Could you assign a variable to the let expression? So the let block has a value. The value is the value of the last expression in the let block. The last expression in this let block could be my fn, in which case the value of the let would be a function, right? Okay. And yes, you can assign. So yes, all of these are nestable and so on and so forth. This is just a very quick introduction. You'll get to it, but you certainly can write, let, A be let x1, y2, fn if that's not legible, I can stop screen sharing for a second. Let me just stop screen sharing so we can answer that question. Now it should be really big. Now you can see it's super big, right? So yes, you can have a let block that assigns a value to A, that has a let block that assigns values to x and y. The value of this let block is a function of a single variable. Oops. That adds the value of x times the argument value z, y, and this is equivalent to let A be Fn Z of plus 1 times Z2. Okay. Provided that you return A here. Yeah, so Christian, I don't. We haven't talked about immutability yet, so I don't want to. You're rushing the chat in a way that's actually a little bit not helpful there. And I think maybe Haskell syntax can be more clear. Yeah, I mean, I don't think. I personally, it doesn't really matter. The point is, you're going to see stuff like this. I'm putting it in front of you so that when you see the code, you have a chance. The most important thing that you need to know for sure is that the value, like. You can think of S expressions or parentheticals as function applications, and the value of the value of an S expression varies depending on what the special form is. In a let, it's the last value. Generally, it means apply the function to its list of arguments. Cool. And Christian is 100% right. We are also going to treat our languages as being how do you say it? As all data structures in our language as being immutable, but we'll get to that in just a second. I don't know why I share screen again. Okay, back to it. Speaking of, we got just ahead of things. So in our languages, although it doesn't necessarily have to be the case that the immutable data structures go hand in hand with functional languages, but it's nice when they do, and I would argue more reasonable. We're going to be talking about pure data structures, which is to say that there are no in-place modifications. Like you make a tensor and you can't like go in and change the value of a tensor and then like where you reference it somewhere else. No, you can think every operation returns a copy, or you can think of it as pass by value or whatever, right? So here are some expressions that might start to make a little bit of sense. If you have a list, so this is a list constructor, and this is where the homoiconicity comes in again, right? A list this is a constructor of parentheses 1, 2, 3. That is the syntactic form for list. Let x be a list. Append to x the value 4. Let the value of let is this value, and this is 1, 2, 3, 4. Okay. And you can do all sorts of stuff. So let x be a vector from 1, 2, 3, 4, and then y be last x, and z is a list constructed from the first of x, and a you append to z y, and then you get you add the first of a to the first of rest of a, and that's 5. Okay, great, fine. You'll get it. So they're data structures, vectors. Lists. We'll talk about hash maps. They'll show up in a couple of places as well. They use curly brackets. That's totally fine. But you should be aware that we're going to be talking about and assuming pure data structures in most cases. And what these are it'll become apparent as we go. And I will point out that if you're unfamiliar with pure data structures, or you think it's totally crazy that such things could exist or even be remotely fast or feasible, they're awesome. Like they're worth studying on their own. This is not a data structures course. You should know about pure functional data structures or look them up and understand what they're going on. They're super fast in practice. They're very cool. And they're what make languages like Clojure, in particular, they're what make Clojure an amazing language. And they're intrinsically compatible with automatic differentiation systems, and a good project idea for those of you who are like really into data structures and like computer science might be to apply pure functional data structure ideas to building an awesome tensor processing library for Clojure/Anglican. Okay. Some key ideas to consider about in the language: homoiconicity, the code is data, there are no side effects, an expression and its meaning. This is actually an important thing that I'm saying right now that is something that you might not actually have seen before or thought about, particularly, when you're a mathematician and you're used to applying the rules of mathematics in your head and not thinking about sort of evaluating expressions. Really, like the holy grail of mathematics is actually the evaluation of expressions, and having a mathematically agreed semantics for expressions in some language. The no side effects thing means that there's nothing outside of the system. There's an expression. You can literally take an expression, evaluate it, and then every place you find that expression, you can plug in its value. Or you can, anytime you say let A be something, then you can take that something and put it in place of A everywhere in the scope where A is available, and it will not change the meaning of anything. Okay, that's pretty cool. Except notably things like I/O are side effects. That's confusing, and observe, and we'll get to that later. Cool. Like I said, we're going to go fast and furious, and I really want to get through this language stuff pretty quickly. So for those of you who are not already functional programmers and not already used to this, take a look at this and tell me what either this function does or what we should name it. The function name is not the brain. It's something that you're familiar with, but are we reversing? No, we're not reversing. Note that f is a function. I don't know what rest does. Great, reasonable question. Great, just let's, as much as we can have a conversation, this is like, let's have a conversation. Rest returns all elements of a list except for the first one. First returns the first element of a list. James, map, yes. So what does map do?
It applies a function to every element of the list.
And returns a list of the results of evaluating the function on all values in a list. So if you look at what's going on here, we have an f is a function, values is a list, there's a guard which checks whether or not the list of whether or not the list values is empty. If it is, it returns the list. Otherwise, it prepends the value of applying f to the first element in the list onto the list that is recursively constructed by calling map on, by recursively calling brain on with the same function as an argument and the rest of the values. Okay. So the answer is map. Okay. So the kinds of things that you can write in these languages are very powerful. They're very powerful, higher order functional abstractions that include mapping and other things. I could torture you by asking again what this one should. Yeah, you are doing f on every element of the list. Yes, that's right. So we could. Yeah, let's torture you just to get your brains going and make you think about, look at this kind of code and realize that you're going to have to deal with it. So yeah, what should we call this function? What does it do? So obviously, space shuttle is blocking out the function name, right? So f is a function, x is a starting value, and values is a list. I'll give you that much. I can only see 5 of you, so I can only imagine that the rest of you are as tortured and as the 5 that I can see. I could scroll just to. No, I can't scroll. Sorry.
Frank, I might be entirely wrong about this, but I think first returns the actual value and not a list. So when recalling f of x first values, in the recursive call, the empty function should expect a list, and then I don't think this would actually compile.
It does.
So
but you're looking at the right. You're looking at the right. Okay, there we go. Somebody took the UBC undergrads are coming. Are coming through. Okay. So the point is that if you actually are familiar with these languages, you can actually you can see what's going on. So some people will call this fold. We will call this reduce. Okay, and let's look at a use case of it just for the fun of it, and it's probably a little easier to see what's going to go on here. So you can define a function called sum, which takes a list of items in terms of reducing using the function f starting at value 0.0 over the list of items. Okay, fine. So what ends up happening is this is a recursive call where you call f on the result of calling f here plus on the initial value 0 and the first element of the list. So 0 plus the first element of the list is going to be something, and you recursively call reduce f with a new initial value on the rest of the list. Okay, and when the list is empty, you just return the accumulator x. Okay. All right. So these are, I'm pushing you way forward, but I want to make it clear that like lots of the code examples that we'll look at are incredibly dense, but beautifully expressed using these kinds of operations, like this. Okay, so I don't expect you to be able to necessarily read this now after having done it, having looked at this, but these are the kinds of probabilistic programs that you're going to work with throughout the term. Okay, so this is a program in the higher order probabilistic programming language that we'll get to in a little bit. But just as a rough overview, let's say that there's a function called read data that allows you to read data from a disk. Okay, here we define a function, and we'll talk through what this is in just a second. But also, distributions are going to be first-class objects as well, just like functions are. Okay, so distribution, this is a discrete distribution with some parameters. This is another discrete distribution with some parameters. This is another discrete distribution with some parameters. And this is a vector of discrete distribution objects. These are observation distributions, 3 of them. There's a vector of observation distribution objects. These are normal distributions. These are discrete distributions with the given parameters. Okay. there is an initial state, which is a sample from a discrete distribution with roughly equal probability over 3 values, 0, 1, 2, for instance. And then what this is we use the reduce functionality we just talked about with a function here. Now, we'll look at what this does, where we're reducing over an initial list consisting of only the first state and the data, whatever that happens to be. So we're going to reduce over the data and we're going to accumulate into a list. Okay? But this doesn't look like a function because this looks like a function evaluation. So HMM step here takes transdis and obsdis, which are lists of distributions, and HMM step is a function application. So what's going on? Well, we know that this function application must return a function, and indeed it does. So HMM step takes transdis and obsdis and returns a function, right? That function consumes a state, which will be popped off of this list, right? And it consumes a list of, it takes as an argument a list of states and a list of data, right? And it does the following. It samples a state by getting from the transition distributions, in other words, selecting from the transition distributions the last of the index of the last of the states. This gives you a distribution object from which you can sample, and that gives you the next state. So this is the transition function for an HMM, right? Then, having gotten the next state probabilistically, you observe the data under the observation distribution indexed by that state. Okay. Then you can join or add to the list of states the state that you just sampled. This, by reducing over the data, will result in a list of states. And as we will discover as we go through the term, this program represents in a very generic way the posterior distribution of states in an HMM given whatever data. Okay, so this is now a transportable HMM model. And what's beautiful is, we're going to talk about generative modeling today, but if you understand what an HMM is and you know how to write down such a generative model, probabilistic programming, the tools that you develop and will write probably in homework for this program, probably homework 5 or 6, will automate inference in this entirely. So you don't ever have to think about doing inference. Okay? Is this shocking, scary, relatively clear? I'm trying to point towards the future. I'm going a little bit fast, but it's really like foreshadowing, knowing what's going to happen. I don't expect you to get all of this now. We're going to go through this more slowly as the term goes. You'll return to this and say, oh, I totally get it by about halfway through the term. Yes, no, I'm looking at the chats. Everybody's quiet. We're approaching the Emma Hansen P break. We're not quite there yet. Emma, do you mind me referring to it as the Emma Hansen P break? Okay. This is the Emma Hansen P break. So if everybody wants to take the 5-minute recess, we'll be, what time does this go till? Till 5? Whew. All right. That took a little while. Yeah. Take 5. I'll sit here and take questions, or maybe I will actually take a pee break. I'm not sure. If there are questions, I won't. If there are no questions, I'll take a break. Okay, and now for something completely different. Great. Hey, Vasilius, turn on your camera. I can't see you. You've came on to my list, so yeah, great. All right, thinking generatively. That's what we want to do today. That's really what today's lecture is about. Okay, so we're going to go through a bunch of examples of basically how to think generatively. And this would work so much better if we were in person, so I apologize I don't know how this is really going to work when we're doing COVID. Please pop on. Please, like answer questions. Please be on the chat, so on and so forth. Okay. So we're not going to talk about the programs. Like we've done some nasty syntax, but now let's actually think for a second, right? So a while ago, while I was at Oxford, I was funded by British Petroleum to answer the. Are the slides up anywhere? Yeah, the slides should be online on the course website. I was given the task of weird. Sorry, that's an rsync problem. I don't have the rsync going quite right. They'll be up after lecture, so I guess you have to pay attention. Oh darn. So I was given the task of trying to figure out whether or not effectively oil pipes, but hydrocarbon pipes or whatever, deep sea hydrocarbon extraction pipes would fail. BP funded this research. I think I can say that now. I don't know. Anyway, so they do this crazy thing where they drop a robot way down onto the seafloor where the pipes are, and they wrap it around. They wrap basically a big X-ray, not quite an X-ray, it's gamma rays actually, but whatever. They wrap a big robot around the pipe. They dig around it, and they take an X-ray of the pipe, and they attempt to see whether or not there are internal defects that have been caused by the oil flowing through the pipe that could cause weakening in the pipe that would require them to go down and replace the pipe before there's some sort of horrible environmentally destroying leak. Okay. So the question is, and what we have at the bottom here are actually gamma ray images of pipes where they've put manual defects in. They've put some measuring thickness chocks on there. You can see the little step functions here. These little black lines, these little black things are like little step function. They're little pieces of metal that they stick on that have known thicknesses. And then there are some defects that you can clearly see, which they etched into the pipe themselves. And there are some less obvious defects. Okay. So basically, they take this robot and they go around and they take 1, 2, 3, 4, 5, 6, 7 pictures in different orientations of the same pipe. And then the question is, what's the internal shape of the pipe? What is the internal surface of the pipe actually look like, right? Like it here. Okay. So can any of you write a program to go in that direction? If so, how? I will wait for a little while. Please, please engage. We've got a bunch of these examples to get through, so engage quickly. Program. Just paste them together. Okay. No, so a program to check if the pipe leaks? No, a program to infer the internal surface geometry of the pipe, which then you could use to predict whether or not the pipe would fail if there were thinning. Okay. So I'm asking in this direction. Can you write a program that goes in that direction? The pipe only thins from the inside. In this particular case, realistically, yes. It's the hydrocarbons are high temperature, high flow rates, cold temperatures. There's all sorts of reasons. Yeah. MLE, maximum likelihood estimate. That's out of bounds here. Okay, great. So start with an undamaged pipe and make changes based on what you see. That's a little bit unclear to me. I think there's a way you could possibly do this, right? CNN, okay. I was wondering how long it was going to take. Train a discriminative network if you have enough data. Okay, so how are you going to get enough data here? Right? You can't. Exactly right. You can't. It's not even remotely feasible to think about getting enough data, unless you do inference compilation, which Jason few-shot learning. Again, you can't do few-shot learning unless you have some training corpus that you can learn the overall regressor for. Okay, so the question is, here's the other question. This is the point that I'm trying to get at. Can you write a program to go in the other direction? If I give you the internal surface geometry of the pipe, can you go in the other direction? Payman Bateni says, thankfully he's here, yes. Anybody else? And okay, great. Yeah, it's much easier to envision how to go in the other direction. It's a generative model. You can describe the data generating process. Like you can build some sort of complicated generative model description. Basically, yes, trace rays through the volume. Now the actual physics involved of gamma ray transport through hydrocarbons and iron pipes, it turns out it's not so easy. I even learned a new word when we were doing this called Bremsstrahlung, which is totally weird, and you should look it up sometime if you've never heard of it. Baron can probably actually explain it. I don't even remember what it is, but I remember the word anyway, and I'm probably mispronouncing it because I don't speak German. Baron is typing, it looks like, and I'm looking forward to seeing whatever pops up here. It's an awesome physical thing. Something about something going faster than the speed of light in a particular thing. Yeah. Thankfully, they're physicists, but the point is, right? It's impossible that you can't collect enough data to go in the other direction, right? You can't go from images to the internal surface, but you can go from the some generative model, some program that you write that generates the internal surfaces of a pipe, and then you can use some sort of gamma ray simulation software or whatever you roll your own, something like that, right? So the whole point is that we want to think in terms of, like, if we have a problem we want to solve. Is there going to be an oil pipe blowout, right? We need to solve the problem. In order to solve that problem, we need to know whether or not there's pipe thinning. In order to find out whether or not there's pipe thinning given non-invasive measurements, we have to have some way to go from non-invasive measurements backwards to the pipe geometry, okay? So this is an inverse problem. This is inference. This is so on and so forth. But the way you start with such a problem is that you write down the generative model, okay? And then you use software tools to invert this process and infer the latent variables, here the internal pipe geometry. Okay, so this one's a pretty sophisticated example. How about this one? Okay, this one is going to get all sorts of deep learning people hot and bothered, right? So can you write a program to go from the bottom thing, a CAPTCHA, to the top thing, which is a parsed correct interpretation of the letters in the CAPTCHA? I'm waiting for feedback from people. Okay, so we've got one yes. How is that a question mark? The question mark is we don't know for sure what that letter is, I think, right? There's some uncertainty about what that letter is. But so we've got one yes. So how many yeses, how many no's? Who thinks we can write a program and go that direction? And what form does that take? Yes, using inference compilation. Jason, CNN, good luck handling the noise. Yes, CNN. Okay, but are you really writing the program when you're? So what do you mean by CNN, right? Like, I want to get this sorted out with all of you, right? CNN is not a program. It's a partially specified program structure, right? The program is a generative adversarial network does not go in that direction, right? Okay, so like a CNN is a partially specified program. A fully specified program is a CNN plus data plus optimizer. Okay, that would be a fully specified program. And how are you going to write that down? You can, But in order to write that down, you have to collect all the data and then label it. And that whole collection forms the program, right? You effectively inline that data by learning the weights of the CNN. But the CNN by itself will not solve this problem. You cannot write a program manually to go in that direction. It's very clear that we all understand this. Okay. Okay. Can you write a program to go in that direction? No problem. Yeah, so going in that direction is easy. You start with some string. Here, obviously, the question mark would be filled in with the true character. Who the heck knows what it is? Probably a P or an R, who knows? Then you, specify a noise distribution that hopefully keeps you in the same family as the CAPTCHA being generated. You run this program forward, and you can get a CAPTCHA character, okay? So this is one of the canonical examples of probabilistic programming. And here is the Anglican program for doing something like this. We've done this in a bunch of different languages, so on and so forth. It doesn't really matter. Here we have some procedure for sampling characters. There's a symbol, which is a sample from the uniform ASCII, a position, size, style. Then you sample a CAPTCHA by picking the number of characters. You repeatedly, for that number of characters, call this function sample char. Don't worry that this is a def im rather than a def in. That happens to be an Anglican function, doesn't really matter. You apply some noise, and then you do some other stuff to basically generate the image, and you generate the image, okay? Fine. Then, without training data, right, but instead a well-specified generative model, and well-specified generative model, we all know that there's problems with that, and we'll get into that much, much later on in the course. Provided that the example data comes from, is in the support of the generative model, then solving CAPTCHA, going in the opposite direction, is a matter of performing inference in the generative model. Okay, so here you just saw a sampler, in this particular case, IPM-CMC, applied to the Anglican program that eventually mixes to the correct interpretation of the CAPTCHA. Okay. How about thinking generatively about supervised learning, right? So when we have supervised learning, we can still think generatively, and what we think generatively about is instead of fitting parameters, we specify a prior over them, and this prior often corresponds to some sort of explicit form of regularization, and you generate the parameters of the supervised model, right? And then you fit those parameters via inference, and what you get is something like deep learning. So I'm going to stop sharing screen and go to my fancy schmancy board just for a second, because I can't do it on the iPad, which I plan to do. But I'll do it over here, and theoretically, I don't have to be quite so large. So does everybody know what I mean by thinking generatively about discriminative tasks or thinking generatively about supervised learning tasks? No. Great. Thank you. So let's take regression, for example. So we're going to have our ins here and our outs here, okay? And we'll call this x and we'll call this y just for convenience. And there will be, generally speaking, some provided data set of observations, okay? Fine, all right? Let's pretend that we want to fit a line to this data. So our data is going to be a set, so x, make sure that that stays in range for you. X and y are in R, and our data will be xi, yi. Our data will be a collection of pairs x1, y1, x2, y2, up to x in, y in. Okay? But we want a line, right? So how do we generate a line? What do we need for a line? Two parameters. What parameters? Slope. Okay, fine. So we don't go through all the mumbo jumbo, but we'll say that we want something of the form that looks like this. Okay. Fine. Great. But this generative model is incapable of generating this data. Why is it incapable of generating this data? No, nobody say loss function. There's no loss function. We're not talking about loss functions here, Greg. Come on. Because the data doesn't lie on a line, okay? So really, actually, if we want our generative model to be a generative model of our data, which is what we're always going to be talking about, we need to add something to this. So we just can't have this. What else do we need? Noise, right? Okay, fine. So we need some sort of noise, okay? So now we can maybe generate our data if we can generate all this sort of stuff. And I think all of you have seen this trick before, where we will have W transpose xi1, and W is just going to be MB, okay? So now we have a vector, right? That's fine. Cool. So we almost are there. We almost have a generative model for our data, which will allow us to do inference, right? So we can write down a generative model now for the mathematical object that we're interested in. We can say that W comes from some normal distribution with I sigma squared, something like that. This is a vector. Epsilon comes from, for instance, normal 0, 1, or whatever, sigma epsilon squared. And then that's basically it. This is equivalent to y is distributed normally I about W transpose X xi1 sigma squared epsilon. Okay. So now we have a likelihood. We have a likelihood, which is P of D given our parameters, which are W. We have a prior on our parameters W. This now is a generative model of our data, right? And our inference objective will be P of W given D, which is proportional to the joint, okay? So instead of doing maximum likelihood or putting down some sort of loss function or so on and so forth, we specify a prior. Here's our prior. We specify a likelihood. The likelihood happens to be a conditional distribution. It doesn't really matter. We're just treating the x's as given. That's totally fine. And our likelihood is here, our prior is here, and that's proportional to the posterior. Our inference objective now is to get the posterior distribution over W given our data, which are all the pairs of x's and y's, okay? By putting a prior on our model parameters, we turn a supervised learning problem into an inference problem, okay? So I think if I go back, if there are questions about that, yeah, no questions about that. I guess everybody knows that. That's good. So here is the Anglican higher order probabilistic programming language denotation for the same problem. So here is this is a def query. It doesn't really matter. You think of this as an entire program which takes arguments x vals and y vals. This is called linear regression. It says let m be. You can probably guess what that's going to be. That's the slope. Let c be the offset. F is a function that takes x and returns plus c times mx, which is just the value of a line. And then we map a function, which takes x and y, produces a side effect called observe. This is going to be conditioning under the likelihood, which is normal, about the function applied to x with some standard deviation, where you're observing the value y. You map this function over x vals and y vals, and the return value of this, the return value of this query, the meaning of this expression is the posterior distribution of m and c, the vector of parameters. So this is basically denoting exactly what I have here, okay? And again, if you put this into a probabilistic programming system, you will get a sequence of samples, which is the posterior distribution over model parameters in this supervised model conditioned on data, okay? And again, we're going to talk about less about how to write these programs and more about how to implement the inference algorithms for them, but you should be aware that basically all of the models that you want to write are going to be accessible and denotable in the languages that we talk about, okay? And again, this, I hope how to choose the prior without knowledge of the generating process. Good question. So I think that I'm going through a spectrum of models, starting from places where you know a huge amount about the generating process to situations in which the models are much more generic and you may not know so much about the generating process. However, you might know something about, in this particular case, in a regression setting, in a simple regression setting, you might know something that you want to constrain this to be a positive slope or something like that, in which case you would affect your prior with that knowledge. If you don't have knowledge, then what you fall back on are the standard regularization arguments that you make in machine learning, which is to say that smaller parameter values tend to be better because you end up with more well-behaved regression functions. So, cool. I hope the relationship between this and what has become known as Bayesian deep learning is relatively straightforward. This is just a regression function. There are some parameters. You can lift any maximum likelihood parameter estimation problem in a supervised learning setting into an inference problem. And when you integrate over uncertainty about model parameters, that gives you uncertainty in terms of predictions, and that's basically the basis of Bayesian deep learning, okay? But I want you to think a little bit more broadly about the kinds of generative models that one can write down when you have the tools of a programming language to denote the model, even in the supervised learning setting. So, you know, we're used to mathematical function denotation, some sort of, you know, Dth order polynomial, that's sort of standard, that's fine. But computer languages, in particular, the kinds of languages we just talked about, allow us to write down functions in a different denotation, write them down in a different way. So here's factorial written in our functional programming language. Fine, you know what factorial is, and you can see how it's written here. I don't have to go through it. What about doing something totally crazy and writing and doing basically symbolic reasoning, right, for supervised learning? Let's write down a generative model for source code. Right? It's actually really easy to write down, right? If you write down a grammar for the allowable expressions in that you want to consider in your symbolic reasoning task, say you allow all the mathematical primitive operations, you know, plus, minus, times, divide. There's some terminal symbols, which are the symbol x and the values 0 to 9. There are no floating point numbers, just the integers 0 to 9. And you can construct simple and compound expressions. In other words, E can be rewritten as just as one of the symbols, or E can be rewritten as an operation with two arguments, E, and they're recursively stuck in. And then there's a function. This might not be super obvious. so let me just show you what samples of such functions might look like if you wrote a generative model in one of the languages that we're going to discuss. So here are some functions, right? They're totally reasonable regression functions to think about, and you can think about symbolic reasoning in this way. Basically, this is the way you should think about symbolic reasoning. You have some formal language for describing expressions and functions. This will be useful in any sort of regression or classification setting. Cool. Let me get rid of that. So these are some functions that are generated by this code, and these are in the slides, and we're starting to run out of time, so we'll be very, very quick about this. But this is a stochastic generator of expressions. So these are the operations. You can sample an operation by sampling from a uniform discrete distribution from 0 to count number of operations, and then get the operation out of this list. If you want to generate it in an arithmetic expression, you can sample the expression type from some list where the expression type is, if it's 0, then it's sampling a number from 0 to 1. If it's expression type 1, you get the symbol x. Otherwise, you pick an operation and then you construct a list object. Again, this is homoiconicity going on. Great question. I'll get to it in just a second. Where the list has an operation, which is plus, times, divide, whatever, and then you recursively call generate an arithmetic expression, right? And then you generate a function by making a list with the symbol f in, and then a list of arguments, which is x, and then you construct a list that starts with an operation and then recursively generates expressions, okay? So what are the latents in this case? Awesome. The latents in this case are the expression. They are literally this expression. So when we impose some observations like f of 1, what is a latent? Awesome, great. We're going to get to this in the next couple of lectures. We're throwing stuff at you. We're going to go in the next 4 lectures really slowly through Bayesian inference for those of you who are uncomfortable with Bayesian inference. But a latent is something that is not directly observable. And it is going to be the target of all of our inference applications. In this particular case, the latent, when you're fitting a line, is w, which consists of the slope and the intercept, because we can't see that, but we want to infer it from the data, okay? And this will become very, very clear over the next 4 lectures, basically. Super clear, I promise. So is the structure of the expression also a latent variable? Yes, of course. I mean, the expression has structure, so it's necessarily latent, right? So if you observe, like, say, for instance, 3 points, the true data distribution is actually a line, and you run inference in this generative model with those observations, the posterior samples will be these symbolic expressions, which look like these all evaluate to actually the true data generating distribution in this particular case. Okay, if you actually look at them, these are just unsimplified expressions that correspond to the same thing. Okay, fun. Okay, we can do this for unsupervised learning as well. I don't think I think we will go through mixture models in pretty gory detail, but you can think about how one might write down a generative model for data like this as well. You could describe it relatively straightforwardly, just describe it in language right now. You pick some number of Gaussians, you sample some number of data points from each Gaussian, done. Now you have a generative model. The latents are how many Gaussians are there, what data is assigned to which Gaussian, and so on and so forth, okay? We'll finish up with a couple of other stimulating example applications just to get you to think generatively. And the point about this lecture is to get you to think generatively and to understand that there's a point to coding top down rather than bottom up, particularly if you have the ability to perform inference to go bottom up after you have the top down model specified. So we talked about CAPTCHA solving. In general, whenever you have a scene description, right, you can think of inverse rendering as an inference operation where you have some scene description. On the right-hand side of this slide, we have some a prototypical prior on face geometry in terms of the mesh, a prior on light conditions, and a prior on the texture applied to that mesh, right? Then you can observe a particular face and then try to reconstruct or understand the face via the latent variables, which are the colors on the mesh, the shape of the mesh, and where the light is in the scene. And basically, you can frame rendering is a generative model. Inverse graphics is inference in a generative model that involves rendering. Okay. Another example. This is, I think, probably the most straightforward and obvious example. Is one of my favorites. Daniel Ritchie. I'm a big fan of his work. Directed procedural graphics, right? So if you look on the right, I think that's, I mean, both of these are pretty cool, but the example on the right is I think the most compelling and like it will put your head in the right place, right? So if you're a game designer and you write procedural graphics programs, then that really means that you're writing generative models for physical objects that you eventually render, okay? So let's say that you want to make a forest, and you could either hire a designer to design 1,000 individual trees, or you can hire one programmer to write a procedural graphics program that generates random trees. Grow a segment, split some random number of times, grow those segments, split some number of times, so on and so forth. Okay. The problem arises when you want to, for instance, have the tree grow around these 3 bars for directorial purposes, or go around this logo for whatever reason, right? So you can think about any simulation, and a procedural graphics simulator is a totally reasonable simulator to think about. You're actually physically simulating an object, right? And you would like to have the posterior distribution of simulations that obey some constraints, okay? So it's very, very, very difficult to a priori write a program that generates trees that would avoid these structures. But if you have the tools of automated inference, it's relatively straightforward to write a general purpose tree generation program and then condition on constraints being satisfied or unsatisfied depending on whatever sign you use, okay? So again, the latent here is going to be, just to reinforce this, the latent is going to be the lengths of all the tree branches, the number of bifurcation points, where the bifurcations take place, so on and so forth, the directions that they go. The observation here, the only thing you know is that it shouldn't hit these gray bars, or it shouldn't hit this logo. Okay. And these are samples from a posterior distribution. Here the constraint is make random stable structures out of weird polygonal shapes. So generative model is build weird stacking structures that are stable when stacked together. And they actually went off and built the things that came out. And some of these don't look like they would actually be stable, right? So directed design, if you're like thinking about, like AutoCAD and companies like this are starting to use these tools and techniques quite a lot. I was actually looking at AutoCAD the other night, and they basically do this kind of stuff now. Yeah, well, I think we'll have to leave it here, but this will be the last mind warpy, totally trippy example just to really get you thinking about generative modeling. Why do we have to program? Programming sucks. Wouldn't it be much better to say, I want a program that produces the following result, whatever that happens to be, some characterization of a program output. In this particular case, there's a very crazy thing that we did, which is we said we want to write programs, symbolic programs, programs that look like this, real programs with Lambda abstractions and so on and so forth, that when executed repeatedly, draw samples that are indistinguishable from some reference distribution. Okay? We'll get to examples later on in the course where you have to generate samplers for normal distributions or Poisson variables or so on and so forth. The code that you actually run to draw exact samples from those distributions is rather obtuse. It's not actually that easy. There's, who is it? I think Dijkstra, no, not Dijkstra. Maybe it was Dijkstra. It's not. It's one of the sort of famous 50s, 60s computer scientists' names that has a whole book on how to write programs to generate random variates. But we said, actually, we just want the output of repeated. We want to compare the. We want a program that, when executed, passes a Kolmogorov-Smirnov test of indistinguishability between, for instance, here, a normal distribution. So the distribution that we want is in blue. The prior on code and executions, repeated executions of the code, is shown on the left. Okay, so you see a bunch of programs flashing by really, really quickly. These are samples from a generative model which generates computer code, right? The histograms that you see here in green are the histograms that result from repeatedly executing that code. And on the right, you see an inference sequence running for a long time, attempting to write code that, when repeatedly re-executed, generates samples distributed according to the density of a normal distribution. And we did this for a bunch of distributions, and were able to recover exact samplers for a number of these distributions, which is kind of crazy. How many of you use Excel? Many? Some? Have you ever drug a cell to the right, like put in several values and then drug a cell to the right and had it complete? If you haven't done this, you should do it sometime. This is probably the most widely used application of probabilistic programming in the world. Next to, if you play Xbox, getting your partner's Xbox Live, getting your partner selected, that's also a probabilistic programming application that's been running for a long time. But when you drag a sequence of cells that are partially filled in, like 1, 2, 3, 4, and then it completes at 5, 6, 7, 8, or you put dates in and then it completes the dates in the correct way, so on and so forth, that's called flash fill. That is actually very, 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 very fast program induction a la probabilistic programming of exactly the kind that I just showed you here. Condition on input-output pairs, condition on the next sequence of things, infer the program that would do that, and then run the program to predict the continuation of the sequence. Okay, so there's lots of examples, and we'll go through many, 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 many more of these. People were asking, like, what's the deal, right? It's awesome. You can do all sorts of things. You can frame all kinds of things thinking generatively. You can also totally screw yourself by thinking in this way, right? I'm not saying that this is a panacea that you can solve every problem, not by any stretch of the imagination, right? So this program is the conditional distribution of strings that map to the same MD5 hashed string, okay? So this is the conditional distribution, the posterior distribution of unhashed strings that hash to the same string. Not going to happen. You're never going to solve this problem. This is, it's a non-invertible function, so it's not going to happen. But you can write it, so you can denote things. The question is, can you actually solve the inference problem? We're going to spend a lot of time talking about how to solve inference problems. Okay. So why model-based reasoning? You get interpretability. You get a source of labeled data for training discriminative models. You get regularization. You know something about the computation graph structure, and there's lots of ways to exploit that. That are very sophisticated, we might get to near the end of the term. It allows you to put domain knowledge into the thing. But more importantly, maybe it's actually, despite all of our deep learning training that tells us if we have a bunch of training data and a partially specified programs scaffold, it's actually easier to think and write programs in the generative direction in many situations. Not always, but many situations. So at the beginning of the term, we're going to assume that we can do this, and we're going to talk about doing probabilistic programming in the case where we actually have decent generative models. And there are more examples which you can look at later. Oops, lecture 2 wrap up. That's it. Functional programming. We did some syntax a little bit. Function distributions of values, pure data structures. I put it where I did in the term just to get it in front of you. Do the extra exercises if you want to. You'll notice homework 1 doesn't have it in it. Homework 2, you're not going to have to write any of these programs. You may never even have to write an Anglican program or a Hoppel program or a Foppel program. That's up to you. You will need to be able to actually do inference in them, though. You'll see it's going to be okay. Okay, so but you do need to be able to read them because the book has the examples, and we will show examples in the lecture notes. So you need to be able to at least read them and understand what's going on. Generative modeling, what you should take away today is like the reasonable questions you could ask is, how do I generate or simulate my data? Simulators and generative models do the same thing. Bayesian inference, which are the next lectures, provide methods for answering questions of interest by inferring the unknown latent variables in the model given known outputs or observations. And it's totally reasonable to ask and to think about what happens when you actually don't have a good generative model for the observable data, and how could you possibly learn such a thing. That sort of advanced probabilistic programming, we'll get to that near the end of the term. So for now, we'll assume that we can write down a reasonable generative model, or we can put priors on it and integrate over uncertainty in the parameters, and that's it. So yeah, sorry for running a little bit late, but that's the cost of the P break today. Questions? Thank you. How come we couldn't use a neural network to do the capture problem? You can use a neural network to do the capture problem, right? That's not a problem. But the program is not the neural network. Just to be clear, the program closes over, in a formal sense, the data, right? So in order to actually write the program to solve the capture problem, that program has to have in it all of the data. And that data is, unless you have some access to the capture generator itself, impossible to come by. Do I have formal office hours? No, I have not posted formal office hours. It's totally reasonable to reach out and discuss. I think you have, in your particular case, you have a channel that you can reach out to me anyway. Great. So I will, there will be time. Other questions? Are people running away immediately? I can't tell. Oh, I guess I can. More questions? No? Was it clear? Come on. There's no way it's clear. It's got to be confusing as heck to most people at this point. So there's got to be questions. Ask them. There's no reason not to. Barend, questions?
Sure. Can I ask it not in the chat and just on audio?
Yeah. I mean, there's 13 of us here. Like Tony, Emma.
If you have some
who I can't see, Naomi, who I can't see, Adam, ask.
Or does Baron want to go first?
Yeah. So if you have some bottom up information, say, right? So say you have some part of the inference building blocks. Is there some way to cleverly implement that in this probabilistic programming framework? Can you do that?
Yes, but we're not going to get there for quite a while. Yeah. So there's when we talk about the interplay of inference networks, and basically, eventually, what we're going to get to is that there is a program structure that, no matter whether you're doing neural networks or you're doing, this kind of simulation-based stuff, there is a program structure that is partially specified in both directions, right? In the beginning of the course, we're going to say there's the generative model, and we're going to use arbitrary general purpose inference algorithms. And then later on, we're going to learn inference algorithms that are bespoke to the problem. And then when we start doing that, it will become more apparent how you can use, if you say, for instance, know the conditional distribution of some latent given some observes, how you can integrate that into inference. It will be apparent even in the first homework, where the third homework, where it will be possible to put like proposal distributions in, and using those is exactly where you can put prior information. You can put prior information in two ways, either structurally or in terms of the proposal distributions that you use. Yeah, good question.
I had a question about the example of generating random number generators.
Yeah.
Was the Gaussian distribution easy to generate? Because it seems like like there's a resultant probability theory that sample averages will tend to be Gaussian.
That's called the central limit theorem.
Central
Yeah.
limit theorem, yes. So it almost seems like if you're starting with a random number generator, you can get to the Gaussian quite easily.
That's a really good point. It's actually a really lovely point. So the reason why I'm chuckling is that it's a really lovely point, and it suggests. So the answer to answer your question as straightforwardly as I can, it was a beast and a half to get that. It's actually really, really hard to get that because the algorithms for exact sampling from a Gaussian are like the Marsaglia algorithm or something like that. They're a recursive algorithm, right? That require like 2 random deviate draws, a transformation, and then blah blah blah, so on and so forth, right? I would say that that it's relative, like really. I don't know if you've have heard of what's it called, Kolmogorov complexity.
No.
Okay, so Kolmogorov complexity more or less says like the complexity class of a solution or whatever, like the complexity of a generator has to do with the number of lines of code in some abstract programming language that you need to represent the solution. Okay, so the exact sampler for Marsaglia is a relatively short program. For a normal is a relatively short program, right? Anything that used the central limit theorem kind of idea, in order to be an exact sampler, would be a very, very long program and would require asymptotics, right? Basically, you only get to the central limit theorem kind of thing if you have some sort of asymptotic thing. And the way you get the asymptotic thing would require that you induce a program that has a large amount of data, right? And under the priors for program generation, those priors, if you think about them for just a second, if you already know what a prior is and you understand how you might generate a program from, you might write a generative model for a program. Longer programs necessarily take more random choices to generate, which means under the prior, they have lower probability. So long programs in the Kolmogorov complexity sense are less likely. So even though the central limit theorem idea that you said is really, really interesting, it's very, very unlikely to actually show up as a solution to the problem due to the Kolmogorov complexity, Occam's razor, like low probability under the prior kind of argument. But that's I will admit that we did not look for solutions of that form, and I'm trying to think about whether or not I think they would be accessible under the generative model that we used for programs there, because it was like you can write anything in that basically. Okay, there's lots of stuff on the chat. Namrata, in terms of like being able to actually know who you are, being able to see in terms of like course participation, being able to see you is a big advantage. I don't want to put you in an uncomfortable situation, but I think you asked a question and I would love to actually associate it with a face as well as a name. So in program reduction, do we care about the correct program that generates the data, as there could be a class of equivalent programs that match the given distribution? Absolutely true. And in fact, you saw in the slides that I presented that in the case of this, the posterior distribution puts positive mass on all of these expressions. These are different posterior samples that actually mean the same thing under simplification, right? So we don't particularly care which of those, so long as it has good predictive accuracy, right? And that's also true for instance, flash fill in Excel. We don't care that the exact program is the program, but we care that it generalizes well. So this is absolutely correct. We don't know the correct formula, but we can use prior to prefer shorter sample. Yeah, exactly. Yeah, I see it was also in terms of graphical models and Markov equivalence. Will the Kolmogorov be able to disambiguate in this case? So Kolmogorov complexity and like and and the Bayesian information criteria are very, very closely related, as is evidence under geometric priors. They're all kind of the same thing at the end of the day. But I'm playing a little fast and loose, but not that fast and loose. Or not that loose. More questions? I see Baron's actually like thinking. He's like,
yeah, no, I actually have another question. I was wondering, you mentioned the example of the string hashing algorithm that is not invertible. Is there some way of sort of without trying knowing that something is not going to work? Or do you have to develop some sort of intuition for that? Is there something that we can learn from other things?
There's this whole halting problem thing you've probably heard about. And that you can, like, I have not formally done the reduction, but it would be an interesting, you know, an interesting reduction to do. I don't think it would be particularly hard in, for instance, cryptographic hash functions to show that to know whether or not you can stop is equivalent to solving the halting problem, right? Like, how do you know?
But I guess even if you're not quite in that limit, right? Like there must be some sort of gray area in between where, you know, maybe a function is really hard to invert. It's not impossible, but it's, is there some way of knowing without some other knowledge? Like what would you need to know for it?
Yeah, so I mean, there are diagnostics that you could look at when you're doing inference that would be suggestive of some things. For instance, when we run Markov chain Monte Carlo chains, which we haven't talked about yet, so it's not, sort of not fair, but I think you probably know what I'm talking about there. When you run Markov chain Monte Carlo chains, if, for instance, the autocorrelation time is really, really, really long, right, or rather, you know, if the autocorrelation doesn't decay to zero for very, very, very long periods, then the space is very difficult to mix in, right? So for important sampling-based methods or sequential Monte Carlo-based methods, if the variance of the weights is extremely low, this also is suggestive of a hard problem. I have to think about what a suggested signal would be in variational inference land. Yeah, I actually don't know that there is a good signal in variational inference land. That's maybe one of the holes in variational inference, actually. Yeah, I can't think of one right off the top of my head. Yeah. And I saw your note, Nemrata. Thank you. I appreciate it. Vasilios, anything? No. Tony. All right. Anything else, Baron? Keep going. I'm good. Yeah. Okay, beautiful. Thank you very much. Enjoy your evening. Cheers.